Hello! In this lesson, we will discuss the concept of change of variable, or substitution, which stands as one of the fundamental tools in the realm of integral calculus. The objectives that we pursue are, on the one hand, understanding the change of variable in the calculation of primitives, which would be the method itself, and on the other hand, knowing how to properly apply said method. The basic requirements are to know the concept of primitive and the calculus of immediate primitives. As you all will understand, the more one masters the calculus of immediate and pseudo-immediate primitives, the better. Let's begin by understanding the concept of a change of variable. When dealing with an integral, such as that of a function with respect to a variable t, we might wonder what would occur if we replaced t with something slightly more intricate. In other words, what if instead of t we introduced a function g that depends on a different variable, denoted as g of x? If we know how to calculate the first integral, what will we get if instead of t we have a slightly more complicated function, a function g of x? Well, we would go back to the integral, where there is a t, we would put the g of x, and now we would have a function, f of g of x, which is a composition and which depends on the variable x. However, we see in the first of the integrals that there is a dt. That dt means that we are integrating with respect to the variable t. If now we want to change and we want to work with the variable x, what we have to do is to transform that dt in one way or another. To achieve this transformation, we'll once again utilize the expression and close it within square brackets. Since t is equivalent to week of x, we differentiate both sides to yield dt. When differentiating with respect to t, the result is 1 and dt is retained. Simultaneously, the derivative of g with respect to x is represented as dg by dx, and it is accompanied by dx. This step holds significant importance as it enables us to transition from t with dt to g of x with dx. Once we have already cleared that dt we were talking about, we can come to the other side of the integral and calculate that same expression. Well, what we get there is a kind of a formula that we can learn by heart, and that is actually the change of variable we mentioned at the very beginning. In practical terms, what we call pseudo-integrals are those that are actually being showcased in this last formula that we've just obtained. We have f of g multiplied by the derivative of g. Well, that's exactly the integral of f. If we know how to calculate the primitive of the underscore f, we must know how to calculate the primitive of the expression that we get outside then. Then these, let's say it would be the change of variables of the fundamental tool that allows us to move to the integration to the pseudo-intermediate formulas, but it is way more useful. Let's see an example of how this is applied in pseudo-intermediates. Given this integral, the integral of x multiplied by the root of x squared plus 1, this integral can be rewritten as follows. On the one hand, the square root of x squared plus 1 could be written in its power notation, which would be a function x squared plus 1 raised to 1 divided by 2. Thinking about the formula we have above, we notice that right there we have a function g, which would be x squared plus 1 raised to 1 divided by 2. Raised to 1 divided by 2 would be the function f, and what I need for this formula to make sense is to have in front of it the derivative of what's inside. In other words, the derivative of x squared plus 1. That derivative is 2x. However, I only have x for now. Well, when I am only missing a single constant, as we should already know, what is done is to multiply and divide by the missing constant. In this case, I multiply by 2 and divide by 2, obtaining this result we've got here. Well, what we have in the integral, which is now being highlighted in blue, it is exactly the same thing we have above. This basically is a function g inside a function f multiplied by the derivative of g. Performing the exact same change it is now when we have to make the change of variable. I can say that x squared plus 1, which would be the g, is going to be the new variable, in this case t. We calculate the dt by simply deriving on both sides, and now we swap them. Since this is exactly what we have above, in this case we are left with the 1 divided by 2 that we had out and the integral of f. Then we further simplify until we are left only with the function f. Well, once we have reached this point so far, this function is an immediate function, in other words, an immediate primitive, which is of power type, and we simply apply the rules that we know of the calculus of primitives, which tell us that it would be 1 divided by 2, which is always there, and the primitive of t raised to 1 divided by 2 would be t raised to 3 divided by 2 divided by 3 divided 2. We simplify a little bit more. We must always remember to include the constant of integration. It's important to recall that the set of all primitives of a function consists of the primitive itself plus a parameter, typically denoted as the constant c. After reaching this point, many people think they are already done with the exercise, but they still have one last step, which essentially consists in substituting. Our integral was expressed in terms of x, and therefore the result should also be in terms of x. The final step involves substituting the t with its corresponding change, which is x squared plus 1. We rewrite the entire function exactly as it was, replacing t with x squared plus 1 wherever it appears. Well, so this would be the final result of this integral. Let's see another small example, just so we get to see that the result is not always that straightforward. In this new case, we have a 1 divided by the exponential plus e raised to minus the exponential. If we examine this integral, what steps should we take to solve it? Well, the fundamental method is the change of variable, which essentially involves a change of name, in a sense. We aim to identify distinct components within the integral and assign them a name. In this particular case, we can observe the exponential term occurring multiple times, and our approach involves assigning the exponential, or kernel, the value of t. If we do this in this way, we would have that t is worth the exponential and that the dt is once again the exponential. Let's remember that the derivative of the exponential is the exponential itself. We proceed to substitute them, and it would be the integral 1 divided by 1 plus 1 divided by t, and now it's the turn for the d of x. Once we add the d of x, we notice that for our integral to make any sense should always have to remain within the same variable. In this case, in terms of t, and therefore the d of x has to disappear for it to become d of t. What is the value of dx? Well, its value is 1 divided by t squared. We derive this value directly from the second expression within the brackets by eliminating the dt, eliminating the dx, and considering that the exponent is precisely t. Simplifying, we arrive at this expression here, and this integral here is nothing more than the arctangent of t plus a constant. To conclude, in order to finalize, we need to reverse the change of variable. In this case, we reverse the arctangent of the exponential, adding t. Well, so this has been all what we are able to do after today's lesson. We should know now how to apply the method of the change of variable, which is a fundamental tool to begin to understand that integral calculus is more than an exact science. In a way, it is a bit like an art form in which one has to think a little bit before using any tools or formulas. That has been all. Thank you for attending, students.